So next up, we will have Wojciech Samek from Fraunhofer HHI, and he will be presenting a talk on DeepCABAC, a universal compression algorithm for deep neural networks.
Okay, let me share my screen. Yeah. So can you see my screen? Can you see my screen?
I don't see it yet.
Wait a second. I will try again. Is it working now?
Yes, we can see.
Okay. Yeah, so my talk will be about compression algorithms for deep neural networks, DeepCABAC. So an algorithm which we have developed with colleagues at Fraunhofer Heinrich Hertz Institute in Berlin, Germany. Yeah, as we all know, the complexity of neural networks is growing today. And with that, not only its size, but also like the number of operations needed, and also like the energy needed for performing inference. And while this may not be a problem in centralized setting, where you train your networks on large GPU clusters or do the inference in the cloud, it is certainly a problem in settings like where the processing is performed at the edge on small devices with limited energy resources, with limited battery lifetime, or with limited memory. And also in decentralized learning settings and federated learning, where the learning itself is where the neural networks themselves are kind of communicated, or the update parameters are communicated between clients and servers. So also there, if your networks become very large, you may run into communication overhead problems. So therefore, we need techniques to reduce the complexity of today's models. So by complexity, I mean different aspects. So it can be the size or the memory requirement of a model, or the energy or runtime requirements, or the communication overheads. And in my talk here, I will mainly focus on the size and the communication overheads. So I will leave aside the energy and the other aspects. Yeah, and we are actively working on a new standard on neural network compression. So we mean a group of people at MPEG.
Wojciech, sorry to interrupt. Your
Yes.
slides don't appear to be changing on the presentation.
Sorry?
Yeah, there it goes. Yeah.
Okay. So yeah, we are working on a new standard on compression of neural networks. By we, I mean researchers from different labs, from different companies, and there is a new MPEG standard which will come out next year in April on exactly this topic. And yeah, the idea is to develop a toolbox where we kind of do not define an external format of neural networks, but we are kind of relying on formats such as PyTorch, TensorFlow, on an NX or NNEF. But we kind of want to define independent coding techniques for neural networks in order to very efficiently compress weights, bases, biases, or other parameters of a neural network. And of course, we want to do the compression without sacrificing performance. And yeah, the MPEG standard will have 3 different kind of layers which can be combined. So in the first layer, we will have techniques to reduce the parameters of a neural network, for example, by pruning, sparsification, decomposition, or unification, or other techniques where you kind of pre-process your network in order to make it more compression friendly. Then there is a layer on where we kind of do the quantization, so where we do the lossy compression of our parameters. And finally, some entropy coding, which is a lossless representation. And depending on the use case you have in mind, you can use different combinations of these techniques. And what you get in the end, in the optimal case, is a bit stream kind of defining your compressed neural networks. And the goal is, of course, to reduce the size of this bit stream. And yeah, maybe one final word to this MPEG initiative. There is currently a new call on proposals for incremental compression of neural networks, where we target the federated learning use cases, where we not only want to compress the network itself, but to compress, for example, updates of a network, or parameter updates in federated learning, or updates after with and without network structure changes. So this is something which will be kind of developed in the next year and the next 2 years probably. Okay, but let me go back to DeepCABAC. So the outline of my talk today is I will first give you some background on quantization and encoding. Then I will present DeepCABAC as a new universal technique to compress neural networks. And finally, also say a few words on our work on compression in federated learning settings. Yeah, so the goal of source coding is to represent a signal with the minimum number of symbols without exceeding an acceptable level of distortion. And practically, you assume that your data, or your kind of your data comes from some stochastic source, so P of W in this case, and then you have some encoder, which consists of a quantization step, which is a lossy compression step, where you kind of reduce the information content in your signal, and then you have some lossless compression step, some binarization, for example, and then you are able to represent very efficiently your parameters of or your signal you wanted to compress. It can be like an audio signal, video signal, or in our case, the neural network itself. And then on the decoder side, of course, you want to reconstruct from the compressed representation, you want to reconstruct the original signal. In the neural network case, this would be the weights of the neural network and the biases, for example. And of course, usually in source coding, people want to minimize the distortion between what you get in the W and what you get out, and the reconstructed Q. So you have some goal, which is to minimize the rate distortion objective, where you have some distortion between the W and the Q. So between the input, the true input of your signal, and the reconstructed one, the quantized one. And you have some term LC, which measures kind of the length of your binary string in this case, which is kind of the rate of your code. So you want to kind of optimize this, both kind of objectives at the same time. And in most cases, like optimizing this is NP hard. Therefore, you have to rely on approximations, or you have to simplify the problem. But we will come back to it later. And from Shannon, we know that the minimum information required to fully represent a sample, that is probability P of W, is of the order of minus P log 2 P of W bits. But in practice, the problem occurs that we really don't. The decoder kind of doesn't know the probability, or doesn't know the probability of your signal source, and also like it may change. It may not be stable. Therefore, although you have like a theoretical measure how to optimally compress, in practice it's often difficult to achieve this compression strength. But luckily, what can in this case, what people kind of developed is some lossless coding techniques which have different properties like universality, which means that the code should have a mechanism that allows it to adapt to a probability model to a wide range of different types, which means that you are not kind of develop codes which only work for one particular probability model, but are able to adapt very quickly. And this is, for example, is a very, very good property and very important property in video coding and in audio coding and all of today's codes. And we use kind of a code CABAC, which has this property for compressing neural networks. Also, minimum redundancy and high efficiency are desired properties. And yeah, well, my colleagues at Fraunhofer HHI are the main developers of video coding standards. So they contributed to all international video coding standards, like H264, H265, or the recent one, VVC. And a few years ago, I asked them like if we can use some of these techniques to compress neural networks, and it turns out that you can. You can, for example, use CABAC, which is a context adaptive binary arithmetic coding tool, in order to highly efficiently encode weights and biases of a neural network. I will come to it in a second how it works. But of course, in videos, there is much more, because videos have a certain structure. You have some correlation between pixels. You have correlations over time. So in videos, you use many other tricks to improve the compression, whereas in neural network, things are a bit more complicated, because also the distortion term in neural network, if you want to compress the weights of the neural network, so in the end, you are not so much interested in having small distortion between your compressed and uncompressed weights, but you want to have a small distortion in the behavior of the neural network, so at the output, which means that, but in this case, like there is some nonlinear accumulation of errors. So if you, for example, compress weights in the first layer, you don't really know the effect on the output. Or you have to take it into account in order to optimally compress your weights. As I mentioned, there is also no clear structure in neural network weights. In videos, you have high correlation between frames and neighboring pixels. And if you think about neural network coding, you have much more flexibility, because you can do some fine tuning after, for example, after sparsification or after quantization. Sometimes it also makes sense to use structural changes. So, for example, instead of encoding a very large neural network, you could use distillation or some other tricks to train a smaller one and then encode the smaller one. So, from this perspective, these two problems are not equivalent, but we can use many of the tricks which have been developed over the last 20, 30 years in video coding for compression of neural networks. And our group in MPEG is exactly like considering this. And DeepCABAC is one of the key tools, key technologies used in this setting. Okay, so how does it work? Yeah, so as I said, we had, if starting from this source coding view, you want to find an optimal code, but unfortunately, this is in most cases NP hard. So what you could do is you could say, okay, I just fix a binarization map and just want to find some optimal quantizer. So you kind of simplify your optimization. And if you would encode in video coding, you could do this, for example, and then you would have the distortion between your input pixels of your input video and pixels of your compressed videos. But as I said, in neural networks, we are not really so much interested into the error between the compressed and uncompressed weight parameters, but we are much more interested in the errors in the output of the neural network. So yeah, so you can kind of rewrite this objective as seen above. So what you want to optimize for is you want to have some quantization. We want to find some quantizer Q, so that kind of the loss between our output of our unquantized neural network, in this case represented by y dash, and the output of our quantized neural network y double dash is kind of minimal, but you also here have some rate term which kind of measures the length of your representation. So as you see, like the y dash kind of depends on the input and also on the original weights w, whereas y2 dash depends on the input but also on the quantized weight. So this is kind of the quantized version of a neural network. And one measure you could use is, for example, you could measure the Kullback-Leibler divergence between these two probability distributions at the output. And you can further simplify by approximating the Kullback-Leibler divergence with the Fisher information matrix. This is something which is kind of well known. And you can further simplify by approximating the Fisher information matrix by only considering its diagonal elements. And what you arrive then, this is at the bottom of the slide, is a weighted rate distortion optimization problem. So where you try to find quantization points for every weight of your neural network, Qi and Wi. So Wi is your weight, Qi is your quantized weight. So you measure kind of the distortions between these two. This is a squared difference, but you weight this distortion by Fi, and Fi kind of tells you how much does this weight has impact on the final output. Which, in other words, if you compress your weight in the first layer, it may have larger impact on the output than when compressing weights in later layers. Therefore, but this Fi kind of takes care of it. But how to get this Fi's? So what we did in our first paper, so by the way, the code is also available at GitHub for DeepCABAC, is to estimate this Fi by if you have like a Bayesian neural network where every parameter where you regard every weight as a distribution, Gaussian distribution with mean and variance. So you could define Fi by 1 over the variance, or y over the standard 1 over the standard deviation in this case. So this would allow to get an estimate for this impact. So how impactful are these particular weights on the prediction? And as quantization points, you could very simply just take like a uniform quantization and like just some step width where you have your quantization points along some step function with some particular step size. So in this case, you just have like one free parameter, which is the step size in your optimization. And yeah, as I said, the key of this is like the lossless quantizer CABAC. And you can further simplify, for example, this is the first version of DeepCABAC which we tried, and further we kind of just simplified and just saw what happens if we just use simpler uniform quantization and afterwards apply DeepCABAC. So we get we get rid of all these problems with estimating the Fi, and it's when choosing the rights, we didn't expect it, but it also works quite well. So it seems that the main compression strength comes from CABAC, from the lossless part in this case. Therefore, I would like to very briefly tell you something about CABAC. So how can you imagine how it works? So it's like a binary arithmetic coder with some context. So what you need to do at first, if you apply CABAC, is to binarize your value. So for example, if you want to encode a weight parameter of 1, then you binarize it in binary symbols, in this case 1, 0, 0. And how do you do this? You have different decisions to take. So for example, the first decision is a sign flag. So as you see here, everything which is non-zero gets a bit 1, and only the 0 gets a bit 0. So since 1 is not 0, it gets a bit flag 1, and then you get to the next decision. The next decision is the sign decision. So everything which is negative gets a bit flag 1, and everything which is positive gets a bit flag 0. And 1 is kind of positive, therefore you get like 0 at the second position. And then you have the decision absolute greater than 1. And so which means that everything which is greater, absolute greater than 1 gets a bit 1, everything else gets a 0. And since 1 is not absolute greater than 1, you get a 0 at the end and you are done. So you kind of, the symbol which you encoded here, like 1, you first represent in a binary, as a binary term, 1, 0, 0. And then you apply some smart arithmetic coding techniques, or a smart arithmetic coder. But in this case, why is it smart? Because it uses some context model. In other words, the probability model of each decision which you take can adapt, and it adapts on the fly on the data, on the statistics of the data it has seen. And by this property allows you to accurately accurately encode any distribution around 0. So for example, here we saw that most of quantized neural networks have this kind of weight distribution. So it's kind of distribution around 0. It's not necessarily a Gaussian distribution. It can also be tilted to one of the sides. But with this adaptivity, you can very efficiently encode these parameters, because your probability model continuously adapts. And arithmetic coding is also a very efficient coding technique, so you get minimal redundancy and also high efficiency. And with all this machinery, you can encode, for example, VGG16. You can reduce its size from 550 megabyte to 8.7 megabyte, or ResNet 50 from 102 megabytes to 4.8 megabyte without losing any accuracy. And you can, in this MPEG standardization, we have like, I think, 5 or 6 different models. So these techniques are developed so that they also work for other kinds of networks, also like for mobile net or for more state-of-the-art networks. And there are also many other tricks which we developed in the last runs in the last kind of months and of standardization. For example, you could use local scaling, batch norm folding. You can adapt the block scan order. You can use, instead of uniform quantization, dependent quantization, which is much more advanced quantization technique. You can optimize your QP parameters for all the weights. So there are a lot of tricks we can apply to further reduce the size of this neural network without sacrificing accuracy. Yeah, so this was kind of the one part of the talk. Maybe what just to mention this CABAC, which we use for encoding neural network weights, is not the same one which is used for encoding videos. So the principles are kind of course, the same, but for example, the decisions, the way it works, we have kind of adapted to the distributions which we usually occur when dealing with quantized neural networks. So you have to kind of also like change it and adapt it to the statistics of neural networks. You cannot just use out of the box the same method as for video coding. But as I said, due to this adaptivity and universality, it is a very powerful method to compress and encode neural networks. So for example, in settings where you want to send neural network, or you want to store it very efficiently, or you want to send it from location A to location B, you can save a lot of space and get a model which performs similarly well. Okay, and in federated learning, things go even further, because here you are not just sending things like one time, but you are constantly communicating in neural networks, so updates, parameter changes. You have an upload and download link. And if you would do it like very naively, for example, for VGG16 on ImageNet, if you would communicate all the parameters every round, every step you do, every training iteration, you would end up in like over almost 500 terabytes of communication, which is of course nobody would do, and it would not work out. It would be way too much. Therefore, like of course, you need some kind of compression and sparsification techniques to reduce the size. And yeah, the total communication overhead kind of consists of three factors. So first, like how much you communicate, how often you communicate, communication rounds. You can reduce it by, for example, reducing by not communicating every round, but using some communication delay, for example. The number of parameters you use, so you can use some lossy or lossy compression techniques, and also like the representation of the parameters. And here you can use some efficient encoding, which kind of still reduces the communication size. And this is what we did a few years ago. Actually, the paper was published last year, but I think we developed it 2 or 3 years ago, where you kind of combine a lot of these tricks. For example, you use some communication delay, like in federated averaging. You're not communicating like every round, but after some delay. This reduces communication overhead by a factor of 100 to 1000. Then of course you are not communicating the weights, the full weight matrix, but only the difference with respect to the last, or with respect to your model which you have. Then you can use some other tricks to sparsify the weight metrics. So instead, for example, sending everything, you can just send the largest values or the smallest values, or the largest ones by magnitude. In this case, you would need to send the position of the largest values and also the value itself. And you can further reduce communication by binarizing. So instead, for example, if some of your values in the weight matrix changes, like some of your positive values change and some of your negative values change, you can kind of decide which changes were greater in magnitude and just send the ones which were greater in magnitude. So in this case, you would just need to send the location of the top k largest changes. And we even saw that you don't need to send the respective values, but just like the average. So if you have like, for example, 1,000 parameters, and maybe you just want to send the 10 largest changes, what you do is you select the locations where they are, you send the locations, and just send the average change of these values. And of course, when you do that, you make a large error every time, but luckily there is this mechanism of error accumulation, so you can still get convergence, and it still works if you locally accumulate your errors. And also, like, you can use from source coding some very efficient coding techniques like column coding, which works well for this kind of sparse, geometrically distributed vectors, because you don't need to send the location, but you can compute the difference in the differences in location and then encode it in the column coding sense. Yeah, and we did this and compared, for example, to gradient dropping or federated averaging, and can see that we are like almost two orders of magnitudes better than these techniques. And compared to the naive baseline, we are way better. So, for example, compared to this naive one, you can reduce communication of ResNet 15 trains of ImageNet from 100 terabyte to 3 gigabyte, which is still a lot, I think, but you see that their compression can help help a lot, and we applied it not only like for this one network, but also for different network architectures, and also for different data sets. In all these cases, our sparse binary compression performs better than the baselines. And as I said, the MPEG is currently, or will work on a new kind of compression method for this incremental setting, where you are not compressing the network as is, but you are compressing its state with respect to some older state, like incremental changes. And especially in communications, people in communications, there are many scenarios where these updates matter, and where compression is required. Okay, to summarize, we saw that efficiency, there are different dimensions of efficiency. You can measure it like with respect to storage of your model, memory usage, energy, runtime, or communication overhead. DeepCABAC is kind of a way to reduce the storage and really very efficiently compress your model, and it's based on video coding technology, which is state of the art and has been around for many years, or has been developed for many years. There are also many other options, like, as I said, fine-tuning, neural architecture search. So there are a lot of things you can do in your network compression in addition or instead of applying techniques like DeepCABAC. Also, software co-design is critical. We started recently working on this, have like a paper on this, but this is something which we are still learning more about, how to kind of adapt the compression techniques so that they can be efficiently also used and implemented in hardware. And yes, you saw MPEG is moving forward with standardization, and I hope that this new standard, which will come out next year, will be kind of used by industry and by researchers around the world. And we have implemented some software. We'll release it soon to make these methods also available for using in academic communities. So here are some references to our papers on this topic. Also on federated learning, we have some recent papers, and standardization. And I have also like a website set up, federatedml.org, where I kind of collect all these papers and all my talks, all the slides. So I will also upload these slides there. If you want to have them, you can download them, or you can also find some other information about our work or work which is kind of related to this topic. Thank you very much.
Yeah, thank you, Wojciech, for the great talk. We have, again, we're a little bit early in our schedule, so we have plenty of time for questions if there are any. Yeah, so one question I have, Wojciech, is so after you compress to a bit stream, are you able to say like everything must compress into like at most 8-bit encoding, or is it kind of just like sort of, is there a way to basically constrain that? Because the question is really like, if you look at sort of like a very efficient machine learning, accelerator, for example, like they're basically geared towards doing a whole bunch of computation on sort of uniform sized pieces of data.
Mm-hmm. Yeah, I think, I mean, this compression, I mean, after quantization, of course, you can constrain the quantization to fit, for example, in 8 bits. This is like something which you could do, and you can apply DeepCABAC like on top, because this DeepCABAC is just an entropy coder which converts your quantized representation into a very compressed, very efficiently compressed stream. So I think there is the tasks are kind of a bit orthogonal. Here we are targeting like reducing the size of the network to the most as we can. If you think about hardware implementations, there maybe the objectives you have are different, because you want to, maybe what you want to is to reduce the movement of the data in your memory, or you want to optimize some scheduling of this data movement and also bit width of your representation. So I think some of the things can be combined, but the end goals are slightly different from the work which I presented here, and from research which is going on in hardware accelerators or hardware optimized implementations of neural networks.
See. I think Kushal had another question.
Thanks, Michael. I guess you can hear me. So my question is on the standardization. I think so. Sam, our first keynote, he talked about how they are, exploring different data types on FPGAs. I think similarly, other ASIC, researchers are also trying different avenues. So I just wanted to know that, what are your thoughts on standardization? Because as researchers explore these different data types, it's very difficult to map them to, on more generally available platforms like GPUs and CPUs. So how do you see this converging?
Mm-hmm. I mean, the goals of this MPEG standardization are, of course, to develop methods or techniques, or a toolbox of techniques which is widely applicable. So which is not like optimized only for image neural networks, but which also works on neural networks dealing with audio or some other of text or other data types and content. Therefore, like in the testing and the evaluation which we are doing in the group, we have models and also like coming from different domains. So this is certainly like a goal to develop widely applicable techniques. But I totally agree that this is something which maybe should be a bit more in the focus, because recently a lot of research is reported on image neural networks, and maybe we should set more focus on also like on neural networks and other on other data types and request researchers to report results for the whole range of data types.
Yeah, thank you. That's a good direction. I think, yeah, we should explore all the dimensions on which this standardization banks on, right? So there are quite a few here, in my opinion. So thank you. That's a great talk.
I have a question. Great talk. Very interesting about this approach. So it seems that the encoder-decoder that is applicable for the quantization, it's encoding and decoding appropriately to the model that is target. But I'm curious about to see what is the overhead of these two components. And given the results that you're showing, it seems that the accuracy has not been affected that much, and the reduction of the memory footprint is quite good. But what is the overhead in terms of compute? How long is it taking to do encoder-decoder, depending of the model size that you are applying to?
It is very efficient. I mean, especially this quantization step and the DeepCABAC, the entropy coding step, is very efficient, because also like efficient implementations for these steps exist. Because I mean, in video coding, in the video coding community, people have optimized these methods for many years, and we kind of take advantage of this, that we can, especially in my institute, Fraunhofer HHI, where there is a lot of knowledge about video coding and about optimization. So especially these last two steps are very much optimized. When it comes like to this pre-processing, like sparsification, pruning steps, then it depends like which method you use for pruning, sparsification, but or whether if you apply it or not. But if you want to, for example, apply a state-of-the-art pruning or sparsification method, this may come with some overhead, but the quantization and the coding step is highly efficient.
So just to clarify, so this has been applied to training and inference, or only to one of the other ones?
No, I mean, you have, in this setting, you have your model already trained, and then you want to compress it.
After training.
After training. And I mean, in some of these use cases, depending on what you look at, you may also there may be some validation data available for optimizing some parameters, right? Or for sparsification or for pruning, you may have access to some validation tests, validation set.
Got it. Thank you.
But as I said, there is the code of our, at least on our DeepCABAC implementation is available, and also there will be soon, we will soon release our implementations of the standard. So there will soon be a code available for all the different techniques which have been proposed in the standardization.
I think we had one more question.
Yeah, okay. Hi, Axel here. Thanks for the great talk. In the federated use case, you said something that the Golem coding is good for encoding difference in location and therefore suited. I didn't fully get that one.
Yes,
Can you
yes.
maybe elaborate?
Yes, I mean, here, after the binarization step, what you have is a large vector, or which is very sparse, and where you have only like the positions of the elements which change a lot, right? So the top k, the k largest changes. Mm-hmm. So instead of what you could do, you could, for example, encode these positions by using int16, where you just encode the position location. Mm-hmm. But it turns out that it's much better to kind of instead of having this vector with the absolute position, to convert it to a relative vector where you have like all the differences. So for example, between like the non-zero entry, the first non-zero entry and the second non-zero entry, like how many entries are in between. So you have this difference vector, and you can show that for large sparse vectors, difference vector approaches a geometric distribution. And for geometric distributions, column coding is highly efficient.
Ah, cool. Thanks.
Okay, yeah, thank you, Wojciech, for the great talk again.